Hello, my name is Alfredo Reyes, and I'm going to talk about interpolation theory for the Henstock-Kurzweil Fourier Transform. So the plan of my presentation is the following. First, I'm going to give you some preliminaries, then the definition of the Henstock-Kurzweil Fourier Transform, and finally, some aspects of interpolation theory. First, we have the definition of the LP spaces, where we use the Lebec integral, and it is known that these cushion spaces are Banach for each P. And also, we have the case when P is equal to infinity. And here, we have the definition of the Fourier transform for Lebec integrable functions. Also, by BB, we denote the set of room variation functions over the real line. And in particular, we have the space BB0 of those functions in BB that vanish at infinity. Moreover, HK denotes the vector space of Henstock-Kurzweil integrable function defined on the real line, where it is defined the seminorm of Alexeyevich given by D supremo. And when we consider this quotient space HK over W, we get a norm space. However, this is not a Banach space. That's why we have to consider its completion, which is denoted by this symbol. And by C infinity, we denote the complex valued continuous function on X vanishing at infinity. And we let the sum between L1 plus BB0 as the set of functions which are expressed by the sum of an element on L1 and an element in BB0. In this set of functions, we have the following definition. The Henstock-Kurzweil Fourier transform exists for every s different from 0, and this integral is in the sense of Henstock-Kurzweil. In particular, we study the Henstock-Kurzweil Fourier cosine transform defined by this expression where this integral exists. It is important to notice that for s equals 0 and f living in BB0 may not be defined the value of the HK-Fourier cosine transform in 0 because this integral may not be a real number. That's why we omit the value 0 in the last definition. Now we have the following theorem. The HK-Fourier cosine transform can be extended into a bound linear transformation from BB0 into the space of Henstock-Kurzweil integrable function. And we have that this inequality holds. This is an estimation for the norm. This theorem means that the image of BB0 under the action of the HK-Fourier cosine transform, it is contained in this space. Also, for each P in the closed interval 1, 2, we consider the intersection between LP and BB0 with this norm. And similar, we have this intersection. Notice here that the first one is a set of functions. And here in the second intersection, we have equivalent classes with this norm. Under this condition, we have the following statement. The Fourier cosine transform for the Henstock-Kurzweil integral from this intersection into this other intersection is a continuous map with this inequality holding. Now, an example of a function f that lives in the Henstock-Kurzweil space and in the BB0 space. That's why this integral exists and it is equal to this expression. But as a function of x, is not a member of the space of the Henstock-Kurzweil integrable functions. Therefore, the image of this intersection B under the action of the Henstock-Kurzweil Fourier transform is not contained in the space HK. So we have a different behavior for the HK-Fourier transform with the HK-Fourier transform. Now, I will introduce you some aspects of interpolation theory. First, given two real or complex topological vector space A0 and A1, we shall say that they are comparable if there exists a third space B, which is Hausdorff, and A0 and AB1 are contained in B. This guarantees us that we kept the intersection and the sum between the two spaces. And when we are dealing with norm vector spaces, then we have two norms, one for the intersection and another to the sum. Notice here that for an element in the sum, this element can be expressed as many ways. And when A0 and A1 are Banach space, then the intersection and the sum are Banach spaces. In fact, we have the following proposition. The sum between A0 and A1 is isometric to this quotient space, where D is the set where for the all possible representation for an element in the sum. Now, we shall consider two complex Banach spaces, X and Y, and this strip. And we shall define the complex space F of all functions from the strip into the sum X plus Y, which are allomorphic in the interior of S and continue up to its boundary. With these two maps, continuous. Then in this F space, we define this norm. And the conclusion is that the F space is a Banach space. Now, for each theta between 0 and 1, we define a theta space of all elements in the sum such that there is a function f in the space F that this equality holds, and we define the norm of an element in this theta space by this definition. The importance of this theta space is by this theorem. The theta space is a complex Banach space with this property. It is contained in the sum and it contains the intersection between X and Y, and the inclusions are continuous map for each theta between 0 and 1. Now, the interpolation theorem tells us that if we have two couples of complex Banach space as before, X1, Y1, and X2, Y2, and we have a linear map operator T between X1 and X2 and between Y1 and Y2, then the restriction of this operator to the first theta space, then we get a continuous map from this theta space into this other theta space, where the norm of the operator T restricted to this theta space satisfies this inequality. So, in order to apply this interpolation theorem to the Henstock-Kurzweil Fourier cosine transform, first, we have to consider this product space between L1 and BB0. Here, L1 is a quotient space and BB0 is a space of functions. And then on this product space, we define this quotient space to be the real sum between L1 plus BB0. But we need the complexification of these sums in order to apply the interpolation theorem. And in a similar way, we define the real space L infinity plus the completion of HK and its complexification, given by this symbol. So, when we consider the Fourier cosine transform from L1 plus BB0 into L infinity plus the completion of HK given by this sum, where here we have the Fourier cosine transform for the Lebec integral, and here we have the Henstock-Kurzweil Fourier cosine transform. To summarize, we have the following situation. We have two couples of Banach spaces, L1 BB0 and L infinity with the completion of HK. We take them as complex Banach spaces. Then we have the sum L1 plus BB0 and the theta space of L1 and BB0. We have a map, which is the Fourier cosine transform from L1 plus BB0 to L infinity plus the completion to HK, and this other theta space. So, as a consequence of the interpolation theorem, we have that the restriction of this operator to this theta space, it is a bounded transformation where this inequality holds. And here we have this constant C given by this number, which is the same bounded as before. It is important to say that for each element in the theta space of L1 and BB0, we have an integral representation for the Fourier cosine transform. And it satisfies the Riemann-Lebec lemma that tells us that the Fourier cosine transform vanishes at infinity. Now, I have another example. We have to consider a function h given by this expression. And we notice that in the open interval 0, 1, the derivative of h is given by this formula. And we extend h over the real line as a knot map. Also, we consider a function phi with these conditions in order to have a function f given by the product of h and phi that is a map, a knot map belonging to the Sobolev space W11. Therefore, the HK-Fourier transform of f is well defined and is given by this expression. However, the Henstock-Kurzweil integral of the Henstock-Kurzweil Fourier transform of f does not exist. This means, in symbols, that we don't have this contention. So, the image of the Sobolev space is not contained in the space of Henstock-Kurzweil function, integrable functions. This is a different behavior between the Henstock-Kurzweil Fourier cosine transform and the Henstock-Kurzweil Fourier sine transform. Now, we make a similar analysis when we consider the case of L2 and BB0. So we have to define the sum between L2 plus BB0, and we have to define the space of L2 and BB0 for each theta between 0 and 1. So for the Fourier cosine transform from L2 plus BB0 into L2 plus the completion of HK given by this formula, we have the following situation. The restriction of the Fourier cosine transform on L2 plus BB0 into this theta space is a bound linear operator where this inequality holds. And here we have that C is as before. This factor 2P is as a consequence of the Hausdorff-Young inequality. And it is important to say that here in this theta space, we do not have an integral representation for the Fourier cosine transform due to the definition of the Fourier transform on L2, which is given by a limit process. Now, we consider the case of P between 1 and 2. So we have to define the sum LP plus BB0 and the sum LQ plus the completion of HK. And the Fourier cosine transform on LP is given by this formula. Therefore, as a consequence of the interpolation theorem, we have that the restriction of this operator to this theta space between LP and BB0 is also continuous. And this inequality holds, where here we have a constant gamma P given by the sharp Hausdorff-Young inequality, and C is as before. So here I'll show you some reference. The first one is where you can find the concept of interpolation theory. And in these two papers, there are the properties of the Henstock-Kurzweil Fourier cosine transform. Thank you for your attendance.